So this example, we're on worksheet 8. This is the second day of 3.4. We're going to be asked to solve this equation. E to the 2x minus 3 e to the x plus 2. Most definitely a pre-calc question. It's already done in your notes, so you're just kind of watching me go. And maybe, or maybe not, you look at that question and you think, man, I have a feeling that that thing wants to be factored. Is anybody thinking, yeah, that totally needs to be factored? Not even a little? Okay. So what if I tell you that e to the 2x is the same thing as e to the x squared? So now it kind of resembles something a little better that needs to be factored, right? But a very unusual question because usually you have just x squared or a squared or something like that. So we're going to do a trick here. It's called U substitution, and it's a trick in math where you have a nasty question that you don't like, and you make it simpler for a moment so you can solve it, and then you bring back the nasty part at the end of the question. So we're going to say that e to the x power, I don't want to call it that. I just want to call it a u. The reason they choose u, they use this a lot in calc, and they use the term U substitution a lot in calc. So we're going to kind of stick with that in pre-calc. So like for instance right here, instead of e to the x to the second power, we could rewrite this as u to the second power. And then instead of 3 times e to the x, we could call that minus 3 times u plus 2. Well, now that's looking a whole lot like a trinomial that we could factor. So you guys are going to use your normal factoring techniques, and you're going to rewrite this as u times u, and then how about a minus 2 and a minus 1 for my rest of my factors. So if you were to set this and this equal to 0, you would get u equals 2 and u equals 1. But we don't care about u. That's a horrible thing to say. I know, it's too personal. The variable u doesn't mean anything in this problem. Remember how u isn't even a part of the problem. Go back to the beginning. We originally switched out all the e to the x's for u's. So this really says not u equals 1 and u equals 2, but e to the x equals 2 and e to the x equals 1. So now you're like, well, that's not better. Yes, it is, because you can solve these. This is what we did yesterday. So if I asked you to solve e to the x power equals 2, you would solve it. It's an exponential equation, and you can apply a logarithm or a natural logarithm. Which one would you like to apply in this particular case? A natural logarithm would be beautiful. So when you apply a natural logarithm to both sides of this equation and both sides of this equation, natural log and e will cancel, and you get x equals the natural log of 2. Over here, same thing happens. Natural log and e cancel, and you get x equals the natural log of 1. What we just wrote down are what are called the exact answers to this problem. Those are exact. But on the test, it'll say, what's the exact answer? And then it'll also say, now give me a rounded off answer, like to the 100th place. So I need you to type on your calculator the natural log of 2 for me. Is it like 0.69? Or so? You could steal the answer from up here, I suppose. Oh, they didn't do it. Can someone type the natural log of 2 for me? Okay. So we'll go 0.693. Thousandths place sounds safe. And then natural log of 1, that comes out much nicer. It comes out to a 0. So that was a hoot. That is probably one of the most challenging questions, I think, in the entirety of pre-calc. Like, forget this test, just like in general. You have to know a lot of things, right? So we had to know the trick at the beginning to switch out e to the x for u. And then we had to just do regular factoring. That wasn't too bad. And then we had to come back at the end of the problem and switch back to u substitution so we could actually solve it. We do, but only if it's a logarithm equation. So this was an exponential equation, so you're safe. There's no extraneous solutions for this. Okay. So help me out, guys. I need to know what we've done and what we haven't done. Did we do number 1 in the notes? Yeah. Did we do number 2 in the notes? Yeah. Did we do number 3 in the notes? That's a good one to look at. Okay. So we're seeing another exponential equation. And this time, there's 2 components that are exponential. I don't like that. So check out the bases. If they have common bases, that'll make my work a whole lot easier. Can you think of a common base for a 4 and a 1/2? A 2 would be really, really great. So like instead of a 4, let's call this 4 a 2 squared. And it already had an existing exponent of 3x minus 2. And then instead of a 1/2, Let's call that a 2 to the negative first. And that already had an existing exponent of 2x. So, here's where the mistake is going to happen. When I combine these exponents together, I need to multiply them together, right? Don't forget to distribute it all the way. So, this keeps a base of 2 for now. But his new exponent is a 6x minus 4. Yes, you're supposed to write this down. You're not watching anymore. So then this guy, to his new exponent, if I multiply these together, becomes a negative 2x. So now it becomes a very easy question. In order for these to be the same, that means their exponents have to be the same. So 6x minus 4 has to be the same thing as negative 2x. All right, let's solve. I'm going to subtract 6x over. So next step would be dividing by negative 8. Got to be careful with a little dyslexic over here. All right, so we got x equals 1/2. And you guys asked earlier about, do we have to worry about extraneous solutions? Not in your exponential equations. So, yay. I mean, you're welcome to check it. You might run out of time on your test, but you can check it. All right, 4. So there's a little tech tip over here. It says you can use your calculator to check solutions. Like if you just graph the equation, if it's something that you can graph in your normal equation mode, you can always check your answer. The problem is you won't be able to get exact answers, and that's what I'm looking for on the test. So this number 4 is very much like the example we started today with where you watched me go. It feels like it wants to be a factoring question. This 2 is times e to the x power, but that is being squared. That's what's really going on right here. The e to the 2x can be separated as e to the x squared. And then over here, you got 12 times e to the x, that's fine, minus 54. So this is one of those fun, switch it out for an easier question type of question. So right at the beginning, I'm going to pretend that e to the x power, let's call it a u. So like right here and right here, we're going to switch these out for u's. We are, yeah, we're going to. Good thought though. So this becomes a 2u squared plus 12u minus 54 equals 0. And then had some brilliant advice given to me. They said, while you're trying to solve this quadratic, notice that everything here is divisible by 2. So go ahead and divide everything by 2. So now we have a much easier quadratic to solve. U squared plus 6u minus 27 equals 0. All right, so that's not too bad to factor. We're going to factor this into, let's see, u plus 9. Now do watch your signs on these, because sometimes, like, my amazing PreCalc kids forget how to add. Sometimes I'm that kid, so watch me too. All right, so u plus 9 and u minus 3 are the factors. When you solve each of these factors, that means you get u equals negative 9 and u equals 3. And then you remember, I don't even care about u. Oh, that sounds horrible. I don't know how to word that. U is not the thing I'm trying to solve for. I'm trying to solve for x. And remember, a long time ago in this problem, we said u is really e to the x. So we're going to switch that out. This becomes e to the x equals negative 9. And this becomes e to the x equals 3. Now I got 2 little baby equations to solve. I'm going to apply some type of logarithm. Which logarithm would be best here? Natural log again. So I try to apply a natural log to both sides of this equation. And while this cancels on the left side, tell me what happens when you try to apply the natural logarithm to a negative value. It doesn't work. Natural logarithms are not defined in negative land. So this does not produce any viable solutions. But this side does. So when you apply a natural logarithm to both sides of this equation, the natural log of e to the x cancels out to an x. And then the exact answer that I want to see on your test is the natural log of 3. And then I want you to give me a decimal approximation because you're just typing that into your home script. So what is the natural log of 3? Give me a few decimal places. Can I just say this? Okay. I'm with you. It'll say word around on the test, so. I don't think I gave you any instructions on here. Alrighty. That was a hoot. Oh, it does? Well, perfect. We did that. All right, let's take a look at number 5. I don't think we've done this one yet. So we have 9 to the 2x power equals 12. And at first glance, kids are thinking 9 and 12 have something in common. Mathematically, they do have something in common. The problem is they don't have a base in common. Can you think of any way to rewrite a 9 and a 12 together? Because I can't. No, Adam. No. So now what? Just give up? No, you got to bring that exponent down. What brings exponents down? Logarithms. Okay, your choice. Common log or natural log? That girl. I know I like natural logs. I think we went through this already. Common log works too. Okay, they work the same way as far as the ratio goes. So if we apply a natural log or a common log to both sides of the equation, while nothing cancels, what does happen is this exponent comes down in front of the logarithm. So this becomes 2x times the natural log of 9, which is just some disgusting number, and it equals the natural log of 12. All right, now think about what you're trying to do, guys. You are trying to solve for x. So you're going to have to divide the natural log of 9 over to the other side, as well as the 2. So you're in pre-calc. I think you can handle this, guys. You can do 2 divisions at the same time, either by doing 2 divisions, or you can just take the whole quantity in a set of parentheses. So totally up to you how you get this done. But I do want everyone practice typing this, because typing is kind of the battle here. Sometimes kids are not typing it right, and they don't find that out until they take their test. So everybody type. I want to hear a clickety, click, click, click. It'd be better if your calculator's out and open. Jeez. I have that awkward moment where I'm just waiting for you to type it in now. Is it 0.565? It should come out to roughly 0.565. Okay. Cool beans. All right. So number 6, we have another exponential equation. This time there's a base E problem hidden in there, but I notice it's not isolated yet. So we got to do a little work to isolate it. Oh, that one's kind of boring. Mind if we skip it? Let's look at 7. 3 and 6. There are children out there in the world who will swear up and down that they can rewrite this one as a common base. And I applaud their efforts. I just don't think they're right. Can you guys think of a way to rewrite 3 and 6 so they have a common base? Yeah, me neither. Like 3 to the first is 3, 3 to the second is 9, 3 to the third is 27. Like none of those are 6. So that's not a power though, right? Powers wouldn't work that way. So the answer is no, I can't rewrite them as a common base, which means I'm forced to apply logarithms to both sides. Would you like to use a common log or a natural log this time? Common. Switch it up. All right. So if we apply a common log to both sides of the equation, nothing cancels. So you're probably wondering, why did we do that? Because we got to bring the exponents down. So they come down in front of their own logarithms. So this guy has a 2x out in front of the common log of 3, gross number. And then over here, this is where it gets a little crazy. Your exponent you brought down is a binomial of x minus 1, so you're going to need to put that in parentheses because he's now in front of the common log of 6, but they're being multiplied together. So this is where I kind of give up on like getting the true best answer and just kind of give my teacher a close approximation. Because what's happening here is you've got the log of 6 and the log of 3, which are disgusting, as coefficients. I try to hang out without my calculator as long as possible, and I give up pretty quick on this question. Because instead of writing log 6x minus log 6, can we just type that in our calculator? What is the common log of 6? Give me a few decimal points, place values. I got 1.792. Are you just doing... Oh, no, I'm sorry. No, I didn't. I have natural log on my key. Ignore me. Okay, one more time, Taylor. What'd you get? Give me like 3. 770? Okay. So we have 0.778x minus 0.778. And then over here on the right-hand side, it's a mess, but I have 2 times the log of 3 times an x. So could you multiply 2 times the log of 3 for me? And again, common log, don't pull in a bruise, don't do the wrong logarithm, because you're so stuck in your ways. So 2 times log of 3. 0.954. And there's an x on there. There we go. Okay. Disgusting equation, but we've left it to the thousandths place, so at least like my answer is pretty accurate. If your neighbor kept it to like the 10,000ths place, or even better yet, never truncated a decimal throughout their whole work, they have the best answer. I don't really care. It's not like we're sending people off into space with this math, guys. Let's just get an approximation, okay? Subtract the 0.778x over to the left-hand side. Yeah, I know I'm supposed to be able to do this, but thank you. Just put me out of my misery. Alright, and then it equals negative 0.778. So when you divide both sides by this 0.176. Now I did natural logarithm, but we should still get a very close answer. When I did natural logarithm, I got negative 4.42-ish. What are y'all getting? Yeah. So isn't that beautiful? Don't you just love math when it works out like that? So even though the coefficients were completely different, the ratios of the logarithms ended up being the same value, or close, because we rounded off a little bit. All right, so that's logarithms. Good times. That's exponential, excuse me. Flip to the back. Now let's talk about logarithms. Logarithm functions. And I do want to give you guys a chance to ask questions about homework. So I'm going to skip the examples that are already done for you, and let's just do some that are not done. Okay, so the idea is 1 logarithm per side of the equation, no more. And then once you got that going, you can exponentiate both sides. So that's the word we need to use, okay? Exponentiate. And exponentiate is where you take a base that matches your logarithm, and you shove the base underneath the problem gets hoisted up into the exponent position. That's a legal math move you can do. And the reason we're doing it is to cancel out the logarithm. So these first few questions are incredibly boring because they're considered one-to-one functions where they're both, like, they both have logarithms on both sides. So, by the way, what kind of logarithm do we have here in number 9? It's a common log who has a base of 10. So when you hoist this problem up with a base 10, and I'm just going to write this one out the long way the first time and then probably never again. What you have is 10 to the common log of 3x power equals 10 to the common log of 12. The reason we did that is because common log and 10 will cancel each other out and the 3x will drop down. And then same thing happens over here. Common log and 10 will drop it will cancel out and the 12 will drop down. So that was an incredibly babyish question. I'm sorry to waste your time. The answer is x equals 4. However, this is where you need to watch out for extraneous solutions. The idea is when you plug your solution into the original problem, remember you cannot take the logarithm of a negative value. So if you plugged in a 4 into 3x, that would not be a negative value. So we're okay to keep that answer. On number 10, however, you're not even ready to exponentiate because you can't have log plus log and try to exponentiate that. So what I need you guys to do is I need you to condense this into 1 logarithm. So you got to think about your log rules. What do you do with the inside stuff when you're condensing a log plus a log? Yeah, you multiply them. So multiply them would be 2x. And then on the other side of the equation, it already was a single logarithm, so you don't have to do any work. But this is a base 12 logarithm, so technically what you guys are doing is you're exponentiating with a 12. Because that's what's going to knock out the log base 12. Now, nicely enough, it knocks out on both sides, so everything else just kind of comes out. We have a 2x equals an x plus 7, and x equals 7. Again, I can't be home free quite yet. I got to go back to the original problem and make sure if I plug in a 7, I don't get a negative thing inside of the logarithm. So like right here and right here, if I were to plug in a 7, I do not get anything negative, so I get to keep that answer. We're good with it. All right. Oh, gross. Okay, so here, definitely not condensed yet. I need you guys to condense this log together. It is a common log. Yeesh. What are you guys supposed to do with that inside stuff there? Yeah, you're going to have a trinomial because you're going to multiply it together. Okay. So this would be like the part in my math where I'm worried I'm going to screw it up because it's me. So if I were to multiply these two together, 16x times 20x is 320x squared. And then we have a negative 32x on the outside arch plus a 40x on the inside arch. So that would be a plus 8x in the middle. And then 2 times negative 2 is negative 4. So, what base is this logarithm again? It's a 10, so get in the habit of still exponentiating with the 10, even though you know it's kind of a lame question. And I got nervous at first when I saw this question, because I was like, oh my gosh, I have a quadratic with a 320 coefficient. But if you keep looking in the question, I think there's a lot of simplification that's going to work out in your favor. Like, you can't solve the quadratic until it's in standard form, and it's not even close to standard form, but watch what happens when you do try to get standard form. Bring everything to the left-hand side. So, subtracting 319x squared. And then subtracting the 9x. And then adding the 2. And we have a little baby quadratic, x squared minus x minus 2. Well, that did not turn out how I thought it was going to turn out, so that was good. All right, so we're factoring and we're solving. And such a sigh of relief because this one factored really quite nicely. So how about x minus 2 times x plus 1 as my factors? And then if you go back and you solve your factors, you're going to get x equals 2 and x equals negative 1. And then you're just so stinking happy that it worked out nice. You box in your answers and you walk away and then you get it wrong. Tell me why this is wrong. Okay, because when you plug in x equals negative 1, boom, right there. You get negative 14 when you simplify that. Can you apply a logarithm to a negative 14? No, you cannot. This is an extraneous value. But 2 works, because if you plug in a 2 in either of these logarithms, you get positive values as their algebra simplification, so yay. That is a good time. Here's some good advice for you. Anytime that you're doing work on solving a logarithmic equation and you end up with a quadratic, you're probably going to have an extraneous solution. Not always. Like we saw an example at the beginning of the notes where that didn't happen, but sometimes. All right, so here, log plus log, okay, this, okay, both have to be condensed. So we have a natural logarithm this time. And tell me again what I'm supposed to do to the inside stuff here. I'm supposed to multiply them together. Unfortunately, this is where the mistake occurs. I get kids who tell me x times x plus 16 multiplied together is x squared plus 16. Ah, yeah, there's an x there. So x squared is right, but then plus 16x. They have to remember to distribute the x and all the way through the x plus 16. And then same thing right here. The 8 has to be multiplied into the entirety of x plus 6. So we have 8x plus 48. And this one works out kind of beautiful because when you exponentiate with a, what's the base here? Natural log has a base. E, very good. So using an e to exponentiate, boom. So cancellation happens on both sides. Life is good. You end up with, oh looky, a quadratic. X squared plus 16x equals 8x plus 48. Not in standard form yet. Bring everything over to the left-hand side. So x squared, if you subtracted the 8x over, you still have a plus 8x. If you subtracted the 48 over, you have a minus 48. All right, factoring time. Now, the questions we are giving you on this, they always factor for the logarithm questions. So, well, if it's a quadratic, it'll always factor. So if you got some crazy quadratic and you're like, nothing works, I have to use quadratic formula, you messed up. So we were trying to be nice to you, I guess, in that. It is 12 and 4. X plus 12 and x minus 4 would work. So your solutions come out to x equals negative 12 and x equals 4. And right away, Adam told me no. Who are you saying no to? The negative 12 won't work because, like, boom, right there. If you try to plug in a negative 12, already you got a problem. Now, even though 4 is positive, guys, you still want to go through and make sure it works for all the logarithms. A 4 is good here, it becomes a 20 here, and it becomes a 10 here. So sometimes there's some weird algebra within the logarithm. Like if it said 1 minus x, and you plug in a 4 to that, that's negative. So just watch. Once in a while, they'll sneak in like a weird algebraic within the logarithm, and then you got to think real hard. All right, so x equals 4 is the only viable solution. The other one is extraneous. Don't count it. Looking good? All right, let's talk about some applications. Who doesn't like a nice radioactive decay question? So I think I asked you guys this already, but so far in chemistry, you guys haven't really seen much of this. It is a big component to chemistry when you guys talk about isotopes. And this question is kind of leading into when they do carbon dating for fossils and other other things they find that are buried, in the desert from millions of years ago and things like that. It's also not exactly this technique, but this is the math that's associated sometimes with crime scene investigation and finding not cause of death, but time of death. There's a lot of math involved in that, actually.
We did a little bit of it last year, and we haven't done it this year yet.
In chemistry? Yeah. And I don't know if it's a big part of the curriculum anymore. I mean, no offense to the paleontologists out there of the world and the archaeologists, but it's not like a booming field. There's only so many things they can dig up, It's a cool field, though. Who wouldn't want to dig up old dinosaur bones and things? All right, so the amount of radium A present in a sample after T years can be modeled by that lovely equation, where A sub naught is the initial amount, and then they want to know how long will it take for 50 grams to decay down to 10 grams. So basically, they took a sample, and they're trying to date it backwards, basically. Earlier, when we did this question, something similar to it, we used our graphing calculator, and we estimated via either the table or the graph. Well, that's not good enough now, guys. PreCalc, you should be able to answer this pretty stinking accurately based on the equation. So this guy right here, this is the initial amount, and this is the final amount. So the equation starts off with the final amount. So you only have 10 left after so many years. 10 grams, but you started with 50 grams. Okay. And then it's continual decay, so the base is an E raised to the negative 0.00043 T power. So you guys should be able to solve this exponential equation through our use of logarithms, but not yet. First, I got to isolate the exponential piece. So we're going to divide both sides by 50. Yeah, I'm going to call that 0.2. I mean, this is a real-life question, so you can anticipate the answer is going to be disgusting. It is. Now I'm ready to apply some logarithms. Which one would be best here for this problem? Natural logarithm would be the right way to go. So please apply a natural logarithm to both sides of your equation. On the right-hand side this time, natural log and E will cancel out. On the left-hand side, this is where I need your technology. What is the natural log of 0.2? I don't know either. Something horribly negative and small. That's all I know. Is it negative? Negative 1.61? Okay. So depending on how much truncation you just did with that decimal, you would divide it by negative 0.00043. And if you kept the whole thing on your calculator, like even better, if you just had like natural log of 0.2 instead of rounding and truncating the decimal, you'll get the most accurate answer. And you'll notice with a little bit of truncation, it makes a huge difference in your answer. So like if Piper rounded that off to negative 1.6 compared to somebody who kept everything in their calculator, you guys are going to have a very different answer at the end of this. Could you guys type it with the exact natural log of 0.2? And then I think you get 3,742.9 years. You were a little off, yes. Still a skosh off, huh? I gotcha. And then everybody's favorite logarithm question, the Richter scale. So the Richter scale that measures earthquakes, the intensity of the earthquake, that is a common logarithm. So, I mean, we don't have too many earthquakes here, but I think we've all seen a movie where like they have the seismograph and like you see the little needle like. So the amplitude of that wave is how they're measuring the intensity of that earthquake. So I'm assuming Richter is a person it was named after. I don't really know. I never really investigated the Richter scale, guys. But this is the equation that they've derived through many, many years of science. 0.67 common log of 0.37 times E, which is the amount of energy that the Earth is releasing in kilowatt hours, plus 1.46. And that gives them an estimation on how they can fit in the Richter scale. And again, I don't know a ton about earthquakes, but like this particular earthquake, which measured at a Richter scale measurement of 6, is a moderately severe earthquake, I believe. Like 8 and 9 is crazy, and 6 is it's going to do some damage, right? We had one a few years back. It was like low. It was like a 2 or something, but it didn't even wake me up. And I'm surprised by that. All right, so the Richter scale answer, they actually gave you the answer here, guys. So we're going to put a 6 in for R. And then we have 0.67 times the common log of 0.37 times E plus 1.46. So we're looking for accuracy now that we know how to solve these with math. And the first thing I noticed is we could subtract the 1.46 over. Now this model inherently, it's a fairly accurate model, but the thing is they're comparing earthquakes like on not a very large scale. So when they have this regression model that they derived and it's truncating after like the hundredths place, that's okay. Because like the difference between a 6.2 and a 6.3, like I don't really know how much of a difference there is in earthquake land for that, All right, I need some calculator help though, because apparently I cannot subtract today. This is 4.54, is it? Cool. All right, equals 0.67 log, common log, of 0.37e. And I'm trying to solve for this e, but I'm not ready to work with the logarithm quite yet. Let's divide both sides by 0.67. And now I give up on my mental math. Can y'all tell me what 4.54 divided by 0.67 is? 6.776. Thank you. And it equals the common log of 0.37 times E. So I'm trying to solve for the amount of energy that this guy released during the earthquake. And it's embedded within a common logarithm. What is the base of a common logarithm? So we need to exponentiate with a 10. So 10 to that power, and then 10 to this power over here. These guys cancel, and this is something horrendous on my calculator. I don't have any idea what this is. Don't even type it yet, guys. I mean, you can type it, but you still have one more step. What's the last step we have to do to solve for E? Divide by 0.37, yeah. So this, on my calculator, is the amount of energy that the Earth released during this earthquake in kilowatt hours. Now, this is a big old number. I just want you to start listing me out the digits that you see. Don't even try to like put commas in. Just digits. Go. Wait, hold on. One person. And then kilowatt hours. Woo. I have no idea what that means. Like, I don't have any comparison for what a kilowatt hour looks like or feels like, I guess. Yeah, it's that. So I guess the answer is a lot of energy. I mean, you got to think it's like the Earth moved. That's big, man. Okay, so for tonight, you guys have, what? Oh, more than 10 minutes. Okay. If you didn't do last night's homework on worksheet 11, I think that would probably be the easiest thing for you to work on right now. So worksheet 11, side B, you guys were asked to do the circled questions. Those were the little baby algebra 2 questions from last year. So that was your warm-up assignment to get ready for today. Today, you can officially finish page 196, and then you can also do page 167. It's all attached into the same Google Classroom, into this bookwork. Page 167 is first. Those are all the applications that like we just did with the Richter scale and stuff. And then if you keep scrolling down, you'll see page 196, which is all the algebra stuff. Okay, so it's not a ton of questions. Every assignment is like 8, and then that's it. Okay? But I heard there's some homework questions. I'd love to look at them. Like what, my dear? Am I looking on worksheets right now? Okay, worksheet 5A. Oh, that's a great one to ask questions on. Thank you. Okay. So, worksheet 5A, which number are we looking at? 2? 2? Did we have to do 2? I mean, we can
Was
look
it
at
this sheet
two.
that you switched them up on, or is that another one?
It's whatever's on your homework check. Someone have a homework check handy? Oh, you're doing 1, 3, 5, 6, 7, 8, 9. So you want to look at a different one from that list? 5, okay. So, number 5. The atmospheric pressure is 14.7 pounds per square inch at sea level. It's reduced by half for each 3.6 miles above sea level you go. All right. So this rule works for altitudes up to 50 miles. So what the formula they want you to use, and it is on that, I don't know what color it is for you guys, but you had like those weird formulas. You get a card when you test. I wrote it at the top of my paper when I started keying this worksheet up, and it looks like this. N equals N sub naught times whatever your rate is to the T over H power. And this formula works for all of the questions that are on this worksheet that are things like half-life or doubling time, or in this case, the amount it changes per so many miles you go up in altitude, it changes the atmospheric pressure. So that's the formula we're going to use here. So the question is, the pressure is 14.7 right now, so that's going to be my initial amount. And then it's reduced by half. So what goes inside for the R is, we can just put 1/2, or you can put 0.5. Reducing by 0.5 would be like 1 minus, it's 1/2 either way you go. And then T normally represents time. For our problem though, it's measuring how high up you go. So you can call it whatever you want. I'm just going to call it an X. And then divided by how frequently that change occurs. So if you keep reading in the question, it says it reduces by half for every 3.6 miles that you go up in altitude. So that's a 3.6. So on this question, how many feet above sea level is the atmospheric pressure 4 pounds per square inch? They want you to figure out when this comes out equal to 4. So now that you guys just sat through 2 days of equation solving, you can solve this algebraically, right? You can divide both sides by 14.7, and then you can apply a logarithm to both sides. But because I did assign this to you guys early on, it's very possible some of you just interpreted this as I should grab my calculator and graph it and see where they intersect. That's a great way to answer this question, okay? If you guys want to, graph this guy. Oh man, I don't even know what it looks like. But something like this maybe. And then the line of 4, and then you're going to see where they intersect. That would be a fine way to answer this question, because when we originally assigned it to you, you didn't really remember how to solve these. And frankly, this one's really nasty to solve. Now, for the second part of that question, write myself a little note for whoever's absent. Okay, for the second part of that question, what's the pressure in Denver, Colorado? So I need some football fans out there. What's the stadium called in Colorado? The football stadium. Where do the Broncos play? Well, the original name of it. I don't know whoever bought it recently, but anyone know the nickname for Denver? Mile High City? It's Mile High Stadium. Okay, so using that formula, the X represents how many miles in altitude you've gone up, so we're going to just plug in a 1. So in your home screen of your calculator for Part B, you're just going to type a 14.7 times 1/2, either 0.5 or 1/2, use parentheses if it's 1/2. And then to the 1 over 3.6 power. And that's the atmospheric pressure. I think it comes out to 12.1. Yeah? Okay, and then pounds per square inch. I've never been there, but I mean, they say when you watch a football game, oh my gosh, the Bronco fans are going to be mad at me. They say because of the altitude, a lot of things favor athletes in certain sports. Like for instance, they assume kickers who are kicking field goals in Mile High Stadium have a more accurate, making the field goal rate. They're more accurate because of the atmospheric pressure. I don't know if there's truth to that. I mean, there has to be some truth to it. Otherwise, why would they say it? But there's also things that are harder to do up in high altitudes, right? Like breathe. All right. Anything else on worksheet 5? There's some, and I think this formulas guy, that's kind of the key to the rest of the worksheets. Like when you look at number 6, that's the formula you want to use. So maybe real quick, guys, you want to jot down a formula to help you out with number 6 here, or on the back of worksheet 5. says the half-life of a radioactive substance is 14 days. So the initial amount might be changing in the formula, I don't know, but because it's half-life, you're going to throw in a 1/2 for the R. And then if the half-life is 14 days, that's the H. So when they tell you how long it takes for it to cut itself in half, it's 14 days, right? So it's like T over 14. So for those next following questions for number 6, they want you to kind of play with that formula a little bit, like how much remains after 28 days, 100 days, when will it be less than 1 gram. So that's the key to that formula. I think they want you to plug in 4,000 right here. There's 4,000 grams of this material at the beginning of the problem. Okie dokie. Then there's some calculator stuff at the end of that worksheet, some TVM solver. Remember the finance app on our calculator? It's been a while since we looked at that, but that's going to be on our test, of course, so make sure you guys are practicing those. Anything else? Okay, so your job is to catch up on your homework this weekend. We have all applications coming our way on Monday, and then we have a little bit of calculator work coming to our, the very end of the lesson, 3.5. That's the end of the chapter, actually. Regression. It's going to be a good time. Okay. And that's it. And then you got a couple of work days with me. We're going to be doing a lot of application questions over Wednesday, Thursday, reviewing, and then testing Friday. And don't forget, Chapter 2, Expi.